Our next problem is called kth smallest element in a sorted matrix. We are given an n times n, so square matrix, where each of the rows and columns is sorted in an ascending order. We have to return the kth smallest element in the matrix. Note that it's the kth smallest element in the sorted order, not the kth distinct element, so we can have duplicates inside of the matrix. We must find a solution with a memory complexity better than n squared. So basically, if we have this matrix, if we sort all of the elements, we already know that the elements in each of the rows are sorted in an ascending order, and also all the elements in each of the columns are sorted in ascending order. But if we put them in if we transform them and flat out them into array, then basically, if we are searching for k equal 8, so 8th element, we will return 13 because we have 7 elements before it. So it's larger than 7 elements, which basically makes it the 8th smallest number. The second example is less interesting because we are just returning we have a matrix one by one, and we are searching for the first, like the smallest element in the matrix, but because we have only one, we'll just return -5. Now the n, which is basically the length of the matrix, is ranging from 1 to 300, and the elements inside of the matrix can be negative, and they are ranging from -10 to the 9th to 10 to the 9th. And again, we have the reiteration of the fact that all rows and columns of the matrix are guaranteed to be sorted in a non-decreasing order. So they are ascending, but we can have duplicates in the same row or the same column. Then k is somewhere between 1 and n squared. So we are not looking out of outer bounds of the matrix. So if we have 1 times 1, we know that the total number of elements that we have is 1. So we cannot search for k equal 2. So basically second smallest element. Now, because we have this relative sorted order between the rows and the columns, that should be the first hint to use that logic somehow. And when it comes to finding smallest, largest elements, one data structure is really useful, and we have already used it several times, and that data structure is called priority queue. So basically, in the priority queue, we have two things that we have to decide. We have to decide like the initial set of candidates, and then basically replacing the candidates that we are pushing out. So the first set of candidates is pretty easy to notice that like the first row is basically the smallest row. So we have the highest chance to find the kth smallest element if case like sufficiently small in the first row. So the first set of candidates for us will be 1, 5, and 9, for example, in the first matrix. So that's the first row. We'll just copy over the second and the third row. So we will have 10, 11, and 13. And then in the third row, we will have 12, 13, and 15. So basically, we will place the first k elements, assuming that k is smaller than n, which we don't really know because we just know that k is smaller or equal to n squared, but we don't have this constraint too. So we will basically place first k candidates inside of our priority queue. It will be a minimum priority queue, and then if we pull k minus 1 elements from the top of the queue, basically we would using that approach, we would basically inject from the queue the k minus 1 smallest element. So the next element would be at the top of the priority queue would be the kth smallest element. So that's everything is okay, but we now have to figure out how we are replacing the element. So basically, if I am replacing the number 1, which will be at the top of the minimum priority queue when we set basically the first k elements. Of course, in our case, we would place only 3 elements, even if our case equal to 8, because our n is equal to 3, and we are only taking the minimum of n and k. Now, if we want to replace the number 1 because we pushed it outside, and the best candidate, basically, now we are using the relative sorted order of the columns. So the next best element would be 10. So that's the next best candidate. So if we basically keep the coordinates in the matrix of each element, basically the row and the column, and also the value of that element inside of the matrix, then we can use the row and column to basically find the next element. We would be just incrementing the row and keeping the same column. And we continue that until basically we are done with injecting out k minus 1 element. And at the top, after that, at the top of the stack, at the top of the priority queue, we will have the kth smallest element. And because we have inside of the queue, we will have the minimum of k and n, and that's basically that's the relative computation power that we need to use to inject elements from the queue. And we are doing the injection k times, k minus 1 times, so it's relative to k. We will have this time complexity. And for the space complexity, we'll basically have the minimum of q or n, because that will be the maximum size of our priority queue, because each time we are popping out one element and inserting another. So basically the size remains the same. So that's the time complexity for using this algorithm. Now, the second algorithm that we can use to solve this problem is kind of called trial and error algorithm, and it utilizes the binary search. It's one kind of the binary search is always there when we have a ascending order and we are searching for elements. That should be the first idea in your head, that there might be a way to utilize the binary search on certain search space. So in our case, our search space basically the matrix. So if we place if you place the start as the first element of the matrix, or whatever it is, let's just say 1, and if we place end to be the last element of the matrix, which is basically 15 in our case, then basically each time we will be getting a mid element by just using start plus end divided by 2. So basically their average. And then this is basically our trial. We are trialing for this element, for this mid element, to see if it's good enough to be called the kth smallest element. And to do that, we will basically calculate the error for it. And how do we actually calculate the error? Well, basically we have to count the number of elements that are smaller than mid. And how do we count the number of elements that are smaller than mid? Well, basically we can traverse the whole matrix. And in that case, we would have n squared time complexity, because we will have 2 for loops that are just traversing the elements inside of the matrix, and for each element checking it's smaller than the mid. But there is a better way to utilize the shortness of the matrix, because if you are just traversing, we are not utilizing the shortness. So basically, we will start from the first row, so I equal 0, and we will start from the last column, so n minus 1 column, and we will move the j pointer to the left until we find the first element that's smaller than the mid. Because when we find the first element that's smaller than the mid, then basically we know that all of the elements before it are also smaller than the mid. So to our count, we can just basically, in that case, because j will be representing the index of that first element, we will just have to add j plus 1. So if the index is 2, the column is 2, basically there are 3 elements in total in that row that are smaller than the mid. So we can use just the index j plus 1 to basically add the number of elements that are smaller than mid in that specific row. And then after that, we can just go I plus plus and go to the next row. In that case, we will kind of have like a linear time complexity. We'll have basically n plus n, which is 2n, which is basically n. The linear time complexity to search the matrix, because we can move at most n down, and we can move at most n to the left. This is something similar that we have used for searching the matrix problem. So to find an element when there is some kind of shortness inside of the matrix. And once we find basically the count, we will basically check if it's smaller than k. In that case, we know that we are not interested in all the elements that are smaller than the mid, that are equal to the mid and smaller than the mid. So we have to place our start to mid plus 1. Basically, this is our error. And we know that we are not interested in the left side of the binary search, and we are just looking the right side of the search space. So that's one thing. But if count is larger or equal to k, then we know that mid is a potential candidate to be the kth smallest element. So we will just place end equal to the mid. And we will continue this as long as we have the invariant basically start smaller than end. After the loop is done, basically when this invariant is no longer true, basically starts equal to end, and they are pointing at the same mid, that mid will basically represent the kth smallest element in our matrix. Now, we'll just first calculate the time and space complexity for this problem, and then we have one more important question to answer. So the time and space complexity are the following. The space complexity is basically constant because we are not creating any additional data structure. Basically that's the opposite of what you have in the using priority queue. But for the time complexity, basically we'll have log of max minus min, which is basically the search space. This is the search space. So the number of times that we can halve this, basically the range between the maximum element and the minimum element. And then for each of those elements, we are kind of using the counting algorithm that we have already calculated. It's linear. So we'll have n times log max minus min. So what algorithm is better? But that really depends on the initial problem. If we know that k is a lot smaller than n, so it's a lot smaller than n, then we see that the first algorithm is dependent on k. So it's better to use the first algorithm because our second algorithm is dependent on n, or the n dimension. But if we want to optimize for space complexity, because we have, I don't know, like some of the problem is with the space, then they would use the binary search because we have a constant space complexity. It doesn't matter how many elements we have inside of the matrix. We will not create any auxiliary data structures. Now, the important question is actually, how do we know that the mid element exists inside of the matrix? So basically, we have two scenarios. The first scenario is when count is basically smaller than k. In that case, basically our mid is not enough. We know that like we have to move our start position. So that's the first thing. So we'll basically just skip the mid. Even if it doesn't exist, we'll just basically skip it. But if count is larger or equal than k, then we are doing this. We are doing end equal to mid. So we are kind of placing our boundary on an element that might not be part of the search space. But if we basically know that in our case, we will have start, which is basically smaller or equal to mid, and mid will be smaller or equal than end. So if basically we have count that's k plus 1, for example, that means there is an element x that's smaller than the mid and that exists inside of the matrix, and it's also smaller, larger or equal than start. So we kind of have this relation. Basically, if we have an example of x1, x2, and x3, and let's just say that only x1 is inside of the matrix and their relative counts, so the numbers that are smaller or equal to them inside of the matrix are basically k plus 1, and k plus 2. So if we choose mid equal to x2, x2 doesn't exist inside of the matrix, but we know that the count is k plus 1, which basically means that there is an element that's smaller or equal to x2, in this case x1, that exists inside of the matrix, and it's smaller, it's larger or equal to k elements. So eventually, we will basically get start equal to end, we'll kind of shrink this relation, and x will become equal to mid, and start and end will become equal to mid. So basically, that's the convergence. At the end of the loop, all of them will be showing to the mid equal to x1, which exists inside of the matrix, because they are bounded by basically start and end. We are quite sure that they initially that they are inside of the matrix because of the way that we have selected our boundaries. So we will declare n to be the matrix length, and then we will declare our start to be the first element and n the last element of the matrix. So basically the last row and the last column. Next, our invariant is the following. We'll perform the binary search, our kind of trial and error algorithm, where and the invariant will be start smaller than end. For each iteration, we will calculate the mid element, and for each mid element, we will calculate the number of elements that are smaller or equal to mid. We'll start with the first row and the last column, and we will basically move as long as I and j are in the boundary. So I is smaller than the number of rows, and j is larger or equal to 0, because we will be moving j in the opposite direction, basically to the left. So we will be decrementing it instead of incrementing it. So basically, we will first search for the element inside of the current row that's smaller than the first element that's smaller than the mid. As long as we have elements that are larger, we'll just decrement the j. And once we find it, basically we can we can use the j index of that element, the first element that's smaller or equal to j, to mid, to add it to the total number of elements inside of the whole matrix that are smaller or equal to mid. And we are not interested in that row anymore, because we have counted all of the elements. Basically, with this little trick, we counted all the elements that are smaller or equal to mid. So we can just go to the next row and we increment our I. And we continue doing this as long as the I and j are inside of the boundaries of the matrix. Finally, we will basically check to which side to eliminate. If count is smaller than k, then basically we have to increment our start to be pointing outside after the mid plus 1, after the mid, so pointing at mid plus 1. So we are eliminating the left side of the search space. Otherwise, we will be eliminating the right side, and we will be placing end equal to mid, because mid is basically our currently best candidate. And as you can see, for most of the problems that we have solved with using the binary search, when we have start is strictly smaller than the end, then basically we have this catching of the best candidate with one of the boundaries. If the invariant would start this smaller end equal than end, then we would basically be searching. We will have the exact search, so we will be returning the exact element that we have found from the loop itself. But in this case, we are not really sure for which element we are searching for. So we have this strict invariant. So this loop will continue as long as that invariant is true. And finally, once it's not true, start and end are pointing at the same element, and that element is basically the mid element that has k minus 1 smaller or equal elements than itself. So we'll just return that element.